For the rest of Chapter 6, we're going to focus on solving equations. 6.2 and 6.3, we're solving trig equations directly, and then in 6.4, we do equations with inverse trig functions. Some reminders as we get started about our college algebra information. Quadratic formula, because we will be using quadratic methods to solve, and if something can't be factored, you have to use the quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. You should have that memorized, hopefully still from college algebra, but if not, refresh your memory. From what we have been doing, think about the periodicity of our functions. Tangent and cotangent are periodic over pi, adjustable by some value. And then the other four, sine, cosine, and their reciprocal functions, are all periodic over 2 pi, adjustable by some value. I was thinking divided by b. They're periodic over 2 pi, so it takes a full rotation on our unit circle to go through one period for sine, cosine, or their reciprocal functions. So just keep that in mind as we solve, so that you can reason through when you need to make adjustments. Okay, solving by linear methods first. So this is our quadratic formula. Obviously not going to start there because we're not going to start with quadratic equations. We're going to start with linear methods. Now, all of these instructions, and I left it like this because that's the way it looks, it's going to look on my math lab, but for all of these instructions, it instructs you to find the solution set over a specific interval, and then for all solutions. Really though, I find my all solutions first. I come up with my all solutions statement first, and then I narrow it down if there's an interval. I look to see how many of those solutions are going to fit in the interval. Now we're going to make use of our restrictions, our conventions and restrictions when we have to use the inverse function values, and we're going to make use of our circle. But remember that these trig functions are angles of rotation, and that every time we come back around, for example, my 30-degree angle, pi 6, has a cosine function value of square root 3 over 2. That is true. If I come back around again and I add 2 pi to that, so this would be 13 pi 6, that also has a cosine function value of square root 3 over 2. And I can just keep rotating around and landing here. I have an infinite set of angles that are going to have this cosine function value. And not just here, but cosine is also positive in quadrant 4. So down here at my other reference angle 30 degrees, 11 pi 6, I have an infinite set of angles that are going to have a cosine function value of square root 3 over 2. So as I'm solving these equations, I need to keep in mind how those reflective properties of my circle. Okay, let's start and walk through it. We're going to solve this equation, 3 tangent theta minus square root 3 equals 0. We're going to find all solutions, and we're going to find the solutions within one rotation from 0 to 360 degrees. Let's start by solving. So our equation 3 tangent theta minus square root 3 equals 0, we want to solve for our unknown, which is our angle theta. Just algebraically, I'm going to move this square root 3 over by adding it. So I have 3 tangent theta equals square root 3. Divide both sides by that coefficient here, so that I've solved for tangent theta. So I've got that tangent theta is square root 3 over 3. Well, this is a special angle function value for my unit circle. So let's think about that. Let's think about, okay, let's see, where is tangent square root 3 over 3? Well, it's not going to be my 45s, and it's positive. Tangent is positive in quadrants 1 and 3. So square root 3 over 3 is going to be, if I stack this one y over x, I would have to rationalize that square root 3. So this is my angle in quadrant 1 where I have that tangent function value. So 30 degrees, let's start there. And I know I'm using degrees because my interval is given to me in degrees. So 30 degrees has that tangent function value. And we reminded ourselves that tangent is periodic over pi. So opposite that, 180 degrees further around, I have another angle that also has a tangent function value of square root 3 over 3. And I can just keep rotating, right? I can keep rotating around. So I could add 180 again, and I have 390, and I add 180 again, and I've got 570, and I can just keep going, positive and negative directions. I have an infinite number of angles that terminate at these two locations. So let's write our all solution statement. Because tangent is periodic over pi, and I can get from one solution to the next just by adding 180 degrees, I can say, okay, well, this equation is true for all angles that are 30 degrees plus any multiple of 180. So I can go in a positive direction or a negative direction as many times as I want from 30 degrees, and it's going to terminate at one of these two locations and pick up every angle. So I need to add to that where n is any integer. That's my solution set for all solutions. Then, so that's B, and then I have my answer for A. What are the solutions between 0 and 360? Well, I've got 30, I've got 210, and if I add 180 again, I'm outside of that interval. So the only two solutions within that interval are those two angle values. All right, let's look at the next one. I see that for this one I'm solving for sine of theta. Well, I'm solving for theta, but I'm going to be using sine. Tangent and cotangent are periodic over pi. Sine and cosine and their reciprocals are periodic over 2 pi. So I'm not going to be able to just start with one angle and add 180 to get all of my solutions. Kind of keeping that in mind. All right, I've got my equation, 2 sine theta plus 1 equals 0. I need to solve for theta. So we're going to start algebraically. I need to move that 1 over, so I'm going to subtract it. So 2 sine theta equals -1. Divide both sides by the coefficient, and I have sine theta equals -1/2. Well, I need to know what angles theta makes this true. Well, let's see. Theta is negative in quadrants 3 and 4, so I'm going to have an angle in quadrant 3 and an angle in quadrant 4. Now, if I had to use my calculator for sine inverse to solve for theta, so theta is sine inverse of -1/2. I'm looking for the angle whose sine function value is -1/2. I would just get this angle down here in quadrant 4 because I have to restrict my inverse function values. But since I got my handy dandy unit circle, where's sine -1/2? Well, it's -1/2 here at 330 degrees, and it's -1/2 here at 210 degrees. So I have a set of solutions that terminate at 330 right there, and I have a set of solutions that terminate right here at 210. Now, the distance between these two angles is not the same as if I keep rotating that same distance here. That happens because I'm dealing with sine, not tangent or cotangent, and so to get from one angle to the next that has that same sine function value, I have to start here and add multiples of 360, or start here and add multiples of 360, because sine is periodic over 2 pi. Sine is periodic over 2 pi. So I have to have both of those as starting places. So my all solutions statement is going to be, okay, all values of 210 degrees plus multiples of 360, or 330 plus full rotations, where n is any integer. So these angles tell me where that terminal side needs to land. And then this bit tells me, you know, I've got angles of rotation. They could just keep rotating if I don't have any restrictions. So I would have an infinite number of angles that land here, because this angle has a sine function value that is -1/2. And I have an infinite number of angles that terminate here, because this angle has a sine function value of -1/2. That's my all solutions statement. I'm also asked for within one interval, or within this interval of one rotation. Well, within one rotation, those two angles are the two that are solutions to my equation. Those two angles will make my statement true. If I kept going, if I added 360, that'd get me to 570. That's outside this interval. Same thing here. All right. So the actual solving is just like we solve any other equation. So you're using your algebra skills, working with trig functions. All right, our title here reminds us, or lets us know, that we're going to be solving by factoring to find the solutions for these angles. Now, one thing to make note of that you need to keep track of, and let's change colors to make it red. Do not divide by a factor. Do not divide by a factor. For example, right here, if I divided both sides by cosine, don't do that. If I divide by a factor, I end up losing a solution. Not they. This will cause you to lose a solution for which the divisor is 0. Okay? So we want to factor to solve, not divide both sides by a factor. Okay, so for example, let's start with our equation. Cosine theta cotangent theta equals a negative cosine theta. We want to solve it. This asks for just over the interval, and we still want to kind of consider our all solutions statement, but we just want the angles within the interval 0 to 360. Now, since I'm not going to divide both sides by cosine theta, let's set it equal to 0 and factor to solve. So if I move this over, I get cosine theta cotangent theta plus cosine theta equals 0. So I added my cosine theta to both sides. Now that I've got it set equal to 0, I want to factor out my common factor. Well, the common factor is cosine theta. So when I factor out that common factor, cosine theta, I'm left with cotangent theta plus 1. Now, just like when we get things factored in college algebra, we would set our factors equal to 0 and solve, because my zero factor property says that if I'm multiplying these two factors together and I get 0, that at least one of them has to be equal to 0. So I'm going to say, okay, well, cosine theta equals 0, and then I've got cotangent theta plus 1 equals 0. All right, so let's think about where these things are true. Let's start with this one. Cosine theta equals 0. Well, cosine is 0 at the pi halves, up here and down here. Now, cosine is periodic over 2 pi, but our quadrantals, we've got this special case going, because if I rotate 180 degrees, I land at another angle that has a cosine function value of 0. So I've got a solution set up here, and I've got an, oh, you know what? We are in degrees, aren't we? So let's change that to 90 degrees. I get my default is radians. So at 90 degrees, my cosine function value is 0. And at 270 degrees, my cosine function value is 0. So that's the important bit that we're interested in. Cosine is 0 here. So if I wanted to make an all solution statement for this, Yes, cosine is periodic over 2 pi, but I can see that because this is a special case with quadrantals, I could start at 90 and add 180. So 90 degrees plus 180 degrees n, where n is any integer, and I'm going to pick up every single one of those angles that terminate at either of those locations. Okay, so let's finish working with this one. We need to solve for cotangent theta. Cotangent theta is equal to -1. So where is cotangent -1? Well, cotangent theta is the reciprocal of tangent, and tangent is negative in quadrants 2 and 4, and it's 1 at the 45-degree angle marks there. So right here at 135, my tangent function value is -1. And down here at the 45 here, so 360 minus 45 is 315, my tangent function value, and therefore my cotangent function value is -1. Now we know that tangent and cotangent are periodic over pi, or over 180. So if I started at 135 degrees and I added rotations of 180, I'm going to pick up every angle that terminates at a place where the cotangent function value is -1. So that's my all solution statement where n is any integer, positive or negative whole number. So that's my all solution statements. Now let's go back and let's focus on my interval. Well, first I've got 90 degrees. And if I want to do all of these, I would add 180 and I get to 270. And if I add 180 again, 270 plus 180 is 450, and that's outside of my interval. So these two angles come from this solution, this factor. And then I come over here and I say, okay, or it's going to be true if my angle theta is 135 degrees, plus 180 brings me around to 315. And if I add 180 again, I'm back around here, but 315 plus 180 is 495 degrees. That's outside of my interval. I've gone beyond my interval. So those four angles, those four values for theta, are the four angles within this interval that makes this equation true. Alright, so we did linear methods, including factoring. Now let's look at our quadratic methods to solve. So remembering, we're thinking about all solutions, and then we're thinking about the solutions in the interval. When we were in college algebra, we did equations of quadratic type, where we use substitution with u. You are absolutely welcome to pull out your trig function and substitute in u if you need that to look prettier, to be simplified while you work with it. You just have to remember to go back and unsubstitute when you're done. We are going to work without the substitution. We're just going to factor. So here's our equation. We've got 3 sine squared x minus sine x minus 2 equals 0. And this is an equation of quadratic type. It's a quadratic equation. This would be 3u squared minus u minus 2. If u is sine x, I would write it as 3u squared minus u minus 2 equals 0, and I can factor that. But then when I'm through factoring it, I have to remember to go back and undo my substitution. So if you're able, go ahead and just work with it in terms of sine x. Alright, so this squared term, I'm going to factor it using reverse FOIL. My signs are going to be different because this constant is negative. To get 3 sine square x, I'm going to have to multiply 3 sine x times sine x. That's what gives me my 3 sine square. And then I know that one's going to be plus, one's going to be minus. I don't know which is which yet. 2 is prime, so that's lovely. So these values are just 1 and 2 or 2 and 1. I've got to figure out which is which. I want to put them in the right orders so that I get this -1 sine x in the middle. Well, since I need to end up with a -1, I know that I don't want to multiply 3 times 2, because 3 times 2 is 6, and then there's a 1, and the difference between 6 and 1 is not a negative 1. So I'm going to want my 2 here and my 1 there. This gives me a 3 sine x and a 2 sine x. So that's good. I need to end up with a negative. So I want my 3 sine x to be a negative 3 sine x and my 2 sine x to be a positive 2 sine x. Negative 3 plus 2 is a negative 1. And then 2 times negative 1 is that negative 2. That's just a little review in reverse FOIL. Again, if you struggle with that, that is definitely something you're going to want to go back and practice. Something else that I just noticed, my interval is given in radians, so my answer needs to be given in radians. Okay, I've got this factored. Just like up here when I got it factored, I use my zero factor property and set each factor equal to 0. I'm going to do that again. I've got 2 factors and I want to set each of them equal to 0 to finish solving. If the product of those is 0, then that means either this factor or that factor or both have to be equal to 0. So we need to find the angles x that will cause this to be true. All right, so to solve for sine x here, I'm going to subtract that 2. So 3 sine x equals negative 2. Divide by 3, I get sine x equals negative 2/3. And over here, I've got sine x equals 1. Okay, so one of these is easier to deal with than the other. When I look at this first one, this is not an angle, a value for sine for a special angle on my unit circle. So we're going to set this aside. I'm going to need the calculator for this. And we're going to look at this one first. So where is sine x equal to 1? At what angle is my sine function value a positive 1? Well, sine is a positive 1 up here at pi half, and that's the only place. Sine is a negative 1 down here, but that's not what I'm looking for. I'm looking for just this positive 1. So this solution at pi half, remember I'm in radians here. If I'm going to do my all solutions statement, my first solution is that every time I come around to pi half, and to get back to pi half, I have to add 360 or 2 pi radians. So plus 2 pi n, where n is any integer. All right, now let's go look at this one. And we got to do a little bit more work with this one because this negative 2/3 is not a special angle. That means that I'm going to have to pull out my calculator. I'm going to have to do some work. Well, sine is negative in quadrants 3 and 4. So I've got an angle here and an angle here, one in quadrant 4, one in quadrant 3, that gives me this negative sine function value. So to solve for the angle, I use my inverse function. So I want to know what is the angle x where the sine function value is a negative 2/3. Now when I plug this into my calculator, it's not going to give me both these answers. It's going to give me this answer because sine inverse is restricted to quadrants 1 and 4. It's going to give me an answer between negative 2 pi half and 0. So let's see what it gives me. We need to be in radians. We're in degrees. Let me switch my mode back over to radians. Okay, so I have sine inverse of a negative 2/3. And this is my radian angle value. Negative 0.7, let's keep 1, 2, 3, 4. Let's keep 4 decimal places for now. Negative 0.7297. Negative 0.7297. Every time I come back around here, I have another solution. So that's going to be my next statement in my all solution statement. Negative 0.7297 plus 2 pi n. I've got another solution over here, right? I've got one more place where when the angle terminates, it has the same sine function value. Sine is negative in quadrant 4. It's also negative in quadrant 3. My calculator just gives me this one. Well, how can I use this to figure out this one? Well, this is how far how many radians I am away from the x-axis. Right there, that's how many radians I am away from the x-axis. So I need to add that on here. This is pi radians, this angle is pi. I need to go beyond pi this far. So I'm going to do, and I'm not going to round here, let's not round, let's multiply this times a -1 to make it positive. I'm going to do this plus pi 3.8713. 3.8713. Does that make sense? Well, pi is about 3.14, so yeah, that absolutely makes sense. That is my third starting place for an angle. So 3.8713 plus 2 pi n, and I have these three locations for angles where they're going to terminate and give me a solution to my equation for all integers values n. For all integers n. For n is any integer. Okay, that's my all solution statement. But that's not what we need. We need solutions within this interval. So we want solutions within my interval. So let's see what we've got. Well, for this first one, we've got pi half. That's between 0 and 2 pi. If I add 2 pi to this, I'm going to be outside my interval. So that's all I get here. For this one, -0.7 is not within my interval. I only have positive angle values within my interval. So we need to go to the next one. So we say, okay, we've got this -0.7297. I need to add 2 pi to that. -0.7297, I go another rotation, I add pi, oops, wrong way, I add pi, and I'm right back here again. So if I have a -0.7297 and I add 2 pi to that, one full rotation, this is the same thing as 5.5535. 5.5535 radians, right? Does that make sense? Well, one full rotation, 2 pi here, would be about 6.28 radians, and so if that is 5.55, yeah, that makes sense. That's a good logical answer. Can I add 2 pi again? Well, no, that's going to throw me outside of my interval. So that's all of this termination point. My third location is here at 3.8713. That's within 0 to 2 pi. Can I add 2 pi again? Well, 2 pi is going to be 6. That'll put me at 9, almost 10, about 10 pi. I mean, not 10 pi, 10 radians, and no, that's outside my interval. So those three angles are going to be the angles within this interval that satisfy my system. Now, as always with rounding, you've got to pay attention to what my math lab wants, how many decimal places they're asking you for. All right, let's look at our next page. Examples 4 and 5. Now we're going to be solving using the quadratic formula. So this is when we have squared equations of quadratic type that won't factor. All right, if we start here, I know I'm going to have to move this 1 over. It's kind of ugly like it is, so let's distribute. Cosine x times itself is cosine square x plus 2 cosine x, and then if I move that 1 over, it becomes a -1 equal to 0. I want to factor that if I can. I can't factor it because of this -1. If that were a positive 1, it would be a perfect square trinomial. It's not. This is not factorable. There's no way to get real number factors that are rational factors that are going to work. So I have to use my quadratic formula. Remember, x equals -b plus or minus square root of b squared minus 4ac all over 2a. So that's my quadratic formula that I'm going to be using. So I'm solving for cosine x. -b is this -2 plus or minus square root of b squared minus 4a is the coefficient here, so a is going to be 1, c is -1 all over 2a. So I've got negative 2 plus or minus square root of 4 plus 4, because a negative and a negative is positive, all over 2. Order of operations, make sure you're paying attention while you simplify. 8 is not a perfect square, but it has a perfect square factor. Square root 8 is the same thing as square root of 4 times 2, and square root of 4 is a 2. So I've got negative 2 plus or minus 2 square roots of 2 over 2. Square root of 8 simplifies to 2 square roots of 2, right there. Now this will simplify because I have that common factor 2 in my numerator. So that will simplify to be negative 1 plus or minus square root 2. If you need a second step here, you can factor that 2 out of your numerator and then reduce. That's the easiest. Well, the easiest would be to split it apart. Negative 2 over 2 is negative 1. 2 square root 2 over 2 is square root 2. Okay, so this is where I get to. I've got that cosine x is equal to either negative 1 plus the square root of 2, or that cosine x is equal to negative 1 minus the square root of 2, neither of which are special angle values on my unit circle. So let's plug these into our calculator and see what they are approximately. So I've got a negative 1 plus the square root 2. Now notice I didn't ask you anything about do I need to be in degree or radian mode, because I'm not using my cosine inverse button yet, so it doesn't matter what mode I'm in. I'm just finding a value for this. And this comes out to be 0.4142 if we're rounding to 4 decimal places, so 0.4142. And here, cosine x equals negative 1 minus the square root 2. That comes out to be a negative 2.4142. Negative 2.4142. Now, stop and evaluate here. Are these both acceptable values for cosine? Well, no. This is outside the range of cosine. This one does not exist. This doesn't work. So my next step is going to be to use my cosine inverse button, so that if I do x equals cosine inverse of negative 2.4142, right here I've got negative 2.4142. If I do cosine inverse of that answer, it tells me domain error. Doesn't work. It's outside the range of cosine, which means it's outside the domain of cosine inverse. So that one does not give me, it's outside the range of cosine, so it's outside the domain of cosine inverse. So that one's a non-starter. It doesn't give me a solution. This one's going to work though. This one is fine. That's between negative 1 and 1. So x equals the angle whose cosine function value is 0.4142. So let's do that. Let's say, okay, well, let's clear this. Clear. Should we be in radians or degrees? It's not telling me, so we're going to do radians here. We're going to do radians. What am I in? I'm in radians. Okay, perfect. So cosine inverse of 0.4142. Here we go. 1.1437 radians. So x is 1.1437 radians, and cosine is periodic over 2 pi, so plus 2 pi n, where n is any integer. So that's my all possible solutions. Now, is that the only set of possible solutions? Well, let's think about it. Because I wasn't given an interval, the solution set is going to be all possible solutions, right? So let's work this out. Cosine. We have a positive cosine function value. Cosine is positive in quadrants 1 and quadrant 4. So I've got angles here and here. 1.1437 radians is right here. This is the one we just worked out. But I also have this one, and I need to figure out what it's going to be. Well, this angle here is the same distance from the x-axis as the angle in quadrant 1. It's this many radians away. So this value, if this is x sub 1, this is x sub 2, it's going to be 2 pi, a full rotation, less or minus 1.1437 radians. So let's figure that out. 2 pi minus that answer gets me to 5.1395. So x sub 2 is 5.1395 radians. So this is one point where the angles terminate and give me that value. This is another angle where they terminate to give me that value. So my second statement, this is x sub 1, x sub 2 is going to be 5.1395 plus 2 pi n, where again, where n is any integer. So those are all possible solutions to this equation. All right, almost done, not far now. We're going to do another example here, and then we're going to kind of put things together in a nice chart so that you have it to look back at if you like that. We're going to solve this one using our trig identities. Notice that when we look at this equation, we've got cotangent and we've got cosecant, and I can't solve with two different trig functions set up there. It's just not going to work. So I need a single function. Let me find an angle. We haven't. So I need a single trig function. Need a single trig function. I can't work in terms of both cotangent and cosecant. Well, cotangent and cosecant, how do those two relate to each other? There's something I can use. Pythagorean identity. My cotangent square plus 1 is equal to cosecant square. So if I square them, I will end up with cotangent square and cosecant square, and I can make a substitution. So that's lovely. That's going to be helpful. Now, remember from college algebra, when you square to solve, you must check your solutions. Because when I square to solve, I may have created an extraneous solution. Something that shows up as a solution, but it doesn't actually work in the original equation. So I need to look for extraneous solutions when I have to square to solve. That's what I'm going to do here, though. I'm going to square to solve. So if I square both sides of my equation, squaring this side, I'm squaring a binomial. So I'm going to either follow my pattern, or I'm going to rewrite it and FOIL it somewhere where I can keep track of it. But I'm going to end up with cotangent square x. Multiply these together times 2, so a negative 2 square root 3 cotangent x. And then square root 3 times square root 3 gives me a plus 3. That's the left side. The right side is just cosecant square x. Now my Pythagorean identity was cosecant square x equals 1 plus cotangent square x. That's my substitution there. So I say, okay. Cotangent square x minus 2 square root 3 cotangent x plus 3 equals 1 plus cotangent square x. Now I just have one trig function to deal with. So let's see what we can do to solve. If I set off and think, you know what, I bet I can move it, set it equal to 0 in factors, quadratic, right? Well, if I subtract cotangent square x, look at that. Those go to 0. Opposites add to 0. So I'm left here with negative 2 square root 3 cotangent x plus 3 equals 1. Now it looks simpler because I've just got this cotangent x to solve for. So let's move our constant over, subtract 3. So I've got negative 2 square root 3 cotangent x equals negative 2. And I'm going to divide both sides by negative 2 square root 3. So I get that cotangent x is equal to a negative divided by negative is a positive 1 over square root 3, which is the same thing as square root 3 over 3. Okay, now we're in business. So I'm looking for the angle x whose cotangent function value. Angle x whose cotangent function value is square root 3 over 3. This is going to be special angles because that's a cotangent value that I identify, that I recognize. So let's think about this. We're not going to need our calculator because it's special angles. I can look at my unit circle. Cotangent is positive in quadrant 1 and quadrant 3. And it's positive square root 3 over 3 where? Well, it's positive square root 3 over 3 at my pi third value. Square root 3 over 3, cotangent, cosine over sine, that goes to the denominator and I have to rationalize, so at pi third. And cotangent is periodic over pi, so that makes life a little easier. So my all values of x such that, let's see, my angles are going to be pi third plus pi n, where n is any integer. So I have some values to check. So let's check some solutions. So my first solution that I propose is when I just n is 0, so the angle pi third. Let's see if that works. When I check, I have to check into my original problem. So I'm going to say, okay, cotangent pi third minus square root 3 equals cosecant pi third. Well, cotangent at pi third, we just said, is square root 3 over 3. Cosecant pi third is the reciprocal of sine, so that would be 2 over square root 3. Right here I need a common denominator, so let's make that 3 square roots of 3 over 3. 1 square root of 3 minus 3 square roots of 3 is a negative 2 square root 3 over 3. And if I rationalize this, that's a positive 2 square root 3 over 3. That's not the same thing. So that's extraneous. That solution doesn't work. And I will give you a hint that once I've got an extraneous solution here, it's going to happen every single time. Every time I land here, that location doesn't work. So this angle, and every time it circles back around to land there, not going to happen. So let's go through and it's going to say, okay, what if n equals 1? Well, if n equals 1, I'm adding pi. Pi plus pi third, 3 pi thirds plus 1 pi third is 4 pi thirds. X equals 4 pi thirds. That's the next one I'm going to check. So I'm looking into my original equation. I've got cotangent at 4 pi thirds minus square root 3 should be cosecant at 4 pi thirds if this solution works. What do I get for cotangent at 4 pi thirds? Well, at 4 pi thirds, my cotangent function value is a positive square root 3 over 3 again. That's why we have that as this proposed solution. And I know that this is going to be minus 3 square root 3 over 3 because I need that common denominator. What about the cosecant function value for 4 pi thirds? Well, cosecant is reciprocal of sine, so that's a negative 2 over square root 3. So in that quadrant, I have a negative cosecant function value instead of a positive cosecant function value. Now we're in business because 1 square root minus 3 square roots is a negative 2 square root 3 over 3. When I rationalize here, I get a negative 2 square root 3 over 3, and that one works. So my solution here, my valid solution, is 4 pi thirds only within that interval that I was given. And if I were not restricted to an interval, I would have the solution set that was this 4 pi thirds plus 2 pi, because it's only when the angles land down here in quadrant 3, so that my cosecant function value is negative, that I get a valid solution. Anytime the angle lands up here in quadrant 1, my cosecant function value would be positive, and it's not going to work. Alright, so yes, there's a lot of moving parts with these solving trig equations. It's going to take a lot of practice. So just make sure you set aside the time for that. You can always use the Show Me a Similar Exercise on my math lab to help yourself get more practice problems. Okay, this is our recap. This is our review of what we've done. The different ways to solve trig equations. First, you need to figure out if it is a linear or a quadratic form, so you know what type of solution method you want to use. If there's only one trig function, you're going to solve for that function. If there's more than one trig function, you need to rearrange the equation so that you've set it equal to 0, and then try to factor so that you can set each factor equal to 0 and solve. If it's quadratic and not factorable, you're going to use your quadratic formula. If there's more than one type of trig function, then try using identities to change the form of the equation, so that, because it might be helpful to square each side of the equation. In this case, you have to watch and check for those extraneous solutions. Okay, now this is the kind of problem solving technique that, working through your options that you did in college algebra, you're applying it here in trig. You know what, this video's been longish. I had this as extra stuff, so we are going to leave this as extra stuff. If you want to look through it, you need to stop and look at think about how many cycles you have here. That's going to help you out, how many cycles. You should end up with a frequency of about 220 hertz, because you're going to take the cycles, number of cycles per second. This is your time. The period, again, is the cycles per second. Or no, period is seconds per cycle. It's the other way around, seconds per cycle. And your period here should end up. But, again, this is just kind of extra stuff. It's good problem-solving application stuff, but we are going to go ahead and wrap up the video here.